What's up guys, welcome back to Dynamic Programming for Beginners. This is part 15 and today we're going to solve another variation of the coin change problem. Before we get started, I would like to review the original version of this problem from lecture number 12, in which we had to find the total number of ways to make a change of size n. Let's say that n equals to 4 and the denominations that we are given are 1, 2, 3 and 5. So the solutions would be 1, 1, 1, 1, right? 1, 1, 2, 1, 2, 1, 2, 1, 1. Notice that 1, 1, 2, 1, 2, 1, and 2, 1, 1 are different solutions. They're considered distinct because we want to count all the possible solutions. 2 and 2, 1, 3, 3, 1 would also be different solutions, right? Now today I would like to review a version of the problem in which the solutions are unique. So if n equals to 4, what would the solutions look like? 1, 1, 1, 1 would stay the same. We can still make this change as it is. Now all of these guys, all these three solutions, we would have to somehow aggregate them, right? Because they're essentially the same, and we would have to, pick one of this. So let's say we'll pick 2, 1, 1. 2 and 2 stays the same. 1, 3, 3, 1, these are the same solutions. So we would also have to pick one of them. So let's say 3, 1 is the solution that we pick. Okay, now we have to follow the framework, right? We have a framework on how to solve dynamic programming problems, and the first step in the framework is define the objective function. But how are we going to define the objective function if we don't know how to solve the problem yet, right? We have different order of how we can start making a change. And we somehow have to incorporate that order into the either problem statement or the objective function itself, right? And the more you practice, the faster you will be able to, find the right approach for this type of problems. But I'm going to show it to you right now. So in this specific problem, since we're given different in the non-unique version of the problem, there are multiple solutions, right? And in this problem, we have to aggregate those solutions. We have to aggregate identical solutions and pick a solution that is most preferable for us. And what is the most preferable for us? Well, we don't know yet. Is 1, 1, 2 the most preferable or 2, 1, 1 the most, preferable? We don't know. Since we don't know, let's answer this question first. Let's say that we always want to choose an order when it's, let's say, not increasing. The reason why I'm saying not increasing is because if the order is, let's say, 2, 2, 3, is this order increasing? No, because 2 and 2 are the same. Order 2, 2, 1. Is this order decreasing? Not really, because 2 and 2 are the same, right? So we want to have an order which is not increasing, meaning that we can have 2 and 2. Is this increasing? No, so it's good. 2, 2, 1. Is this increasing? No, it's good, right? So the order like that is preferable. So what we are going to do, we're going to say that instead of solving the original problem, instead of solving the, I don't have a problem description here, but instead of solving the unique ways problem as it's given in the original description, we're going to slightly change the problem statement, and we want to say that we have to find all the unique ways to make a change of size n when the order is not increasing. And if you do so, apparently it becomes easier to solve the problem. Why? Because this constraint that we just added, we can use it in the objective function. Okay? So, let's say that f of I t is the total number of ways, I'm not going to write everything, so basically is the total number of ways to make a change of size I. And then we also have this t, right? So when the last coin, when the last coin is less than or equals to t. What does it mean? Well, it means that if the change that is being returned is, let's say, 7, 4, 4, 2, 2, 1. So this is in the first state, so to speaking. Let's say this is t, right? What's the next change what's the next coin that we are allowed to return? We can return less than t or equals to t. So we can return either 7 or something that is less than 7. So we can return 4. Now again, 4 is t. What can we return? We can return either 4 or less than 4. So we return 4. And so on. Okay, I hope it makes sense. So this is our objective function. F of it is the total number of ways to make a change, is the unique number of ways to make a change of size I when the last coin is less than or equals to t. Okay, now let's identify base cases. I'm going to clean this part. We no longer need it. Right? Yeah, we no longer need it. So what are the base cases? So let's take a look at f of I 0 when I is greater than 0. How many unique ways to make a change of size I when the last coin equals to 0 or less than 0? There are 0 ways to do so. We can't do it, right? We can't make a change of size. Let's say if I equals to 4 and we're allowed to use, when the last coin has to be 0 or less than 0, we cannot do so, right? Okay, so let's say what's the unique number of ways to make a change of size 0 when the last coin is 0? There is one way. We just return an empty coin, right? Okay, what's the unique number of ways to make a change of size I when the last coin is either 1 or less than 1? So let's take a look. Let's say I equals to 1, right? How many ways to make a change of size 1 when the last coin is 1? There is just one way. There's f, in this case, f equals to 1, because we can use 1 cent and that's it. If I equals to 2, so f of 2, 1, the answer is still 1, right? Because we can use 1 cent and 1 cent. We're not allowed to use 2 cents. 2 cents, right? Why? Because t equals to 1, and 1 is the last coin that we're allowed to use. We can use either 1 or something that is less than 1. So even if I equals to, let's say, 44, f is still going to be 1, right? We'll just use all the ones. Again, that's because the last coin can only be either 1 or less than 1. So f of I1 equals to 1. Okay, now let's take a look at f of I2. When I is greater than or equals than 2. Less than 2, you can write yourself. It's easy. So when the last coin can be either 2 or less than 2, then we have two options. We can start either from 1 or from 2, right? So let's say we start from 2 cents. If we start from 2 cents, it means that we still have to return I minus 2, right? And then what's the last coin that we are allowed to use if we start making a change by using 2 cents? We can still use 2 cents or anything that is less than 2, right? Again, why is it 2 here? If we make a change, so we return some change, right? And then we got to 2. What can we return starting from here? We can either return 2, right? Or anything that is less than 2, right? So we can still keep returning 2's or anything that is less than 2. Now we have to consider 1 cent. So we say plus f of I minus 1. And again, as soon as we hit 1, we're only allowed to use either 1's or something less than 1. And this is basically our transition function. For f of I3, when I is equals or greater than 3, the transition function would be pretty much the same, except we would add I minus 3. So f of I minus 3 plus f of I minus 2 plus f of I minus 1. In which order are we going to solve this problem? We'll have this is a two-dimensional problem. So we'll have a matrix where rows are, let's say, our coins, 1, 2, 3, 5, right? And then columns would be amounts. So we would have 0, would be here, 0, 1, 2, 3, all the way up to the n. So first we would solve the first row, then we would solve the second row. After that we would solve third row. And the answer to the overall problem would reside in the last row, last column. So it would be f of 5n. Let's take a look at the code and see if it makes sense. All right, guys, so here is the problem. Given an unlimited supply of coins of given denominations, find the unique number of ways to make a change of size n. The denominations that we are given are 1, 2, 3, and 5, and then the transition function is when I is greater than 1, f of I 1, f of I minus 1, 1. I is an amount here, and then the second parameter is t. It's the maximum coin that we are allowed to use. When I is greater than 2, we basically add I minus 2. When I is greater than 3, we add I minus 3, and so on. So let's write down the code. We're going to define an DP array which will hold all the solutions to our subproblems is going to be of size n plus 1. I'm going to initialize each row in this DP array. It's going to be of size length of coins, Now I'm going to specify base cases, right? So for each coin, we want to say that the total number of ways to make a change of size 0 for any coin is 1. We just return an empty coin. Now let's return the solution to the overall problem. It's going to be dp of n len of coins minus 1. And we can start writing the main loop. So starting from 0 all the way up to ni++. And now I'm going to copy the transition functions over here so that I could see them. And I'm going to apply it now. If I is greater than 1, dp of I, and then a quick note here. So we are using coin values in here, whereas in code we have to use indices. So dp of I 0 equals dp of I minus 1, 0. And now I'm going to copy all of that because we need to assign dp of I minus 1, 0 for each denomination, right? So we can say 1, 2, and 3, and then we keep going. So for I greater than 2, we will say dp of I 1 plus equals. The reason why I use plus equals is because we need to add previous value. So dp of I minus 2, 1, and now we can copy all of that, and we say 2 here, 3 here. Now, if I is greater or equals to 3, we can copy the last two values, and we say this is 2 here and I minus 3. And we can copy all of that again and apply the same thing for the last bit, which is f of I minus 5, 5. So when I is greater than 5, I minus 3, I minus 5, 3. Okay, so let's try to run test cases and see if the code is correct. Run. Great, so everything is good. Now I'm going to uncomment this piece and write a more general code which will handle different denominations. So I'm going to write a loop over coins which will tackle all of these values, and then an inner loop starting from I all the way up to j, k++, which will calculate the sum of all of these values. So we want to say dp of ij equals dp of I minus coins of k, right? And now we just need to handle a corner case when I minus coins is less than 0. So we say, well, if I minus coins k less than 0, then continue. Let's remove this code, no longer needed, and rerun tests. We need to add plus. Okay, everything is good. And now the last thing that I would like to do here is to review another way to solve this problem. This solution is very similar to what we've done at lecture number 12. Let's take a look. It was the original problem where we had to find the total number of ways to make a change of size n. And when I say total, it means we had to count all the permutations. And the solution was, here is the solution. Basically, we have two loops, and the trick here is that if we swap the loop, coin becomes like external loop or outer loop, then the code will take care of duplicates. So let's take a look how that would work. So I'm going to copy this code here, and I'll rename coin change to coin change unique ways, for instance, and this guy becomes just coin change. And now I'm going to move this loop over here, rerun our test cases, and as you can see, everything is good, right? So why is it happening? Let's take a look at the execution of these loops, right? So let's say that no duplicates. This is when we have this part, right? And with duplicates, it's when we have the opposite. It's basically when it's like so, right? And let's assume that n equals to 3 and the coins, the denominations are 1, 2, and 3. So when we don't have duplicates, the question that we ask is, for each denomination, how many ways to make a change of size 3? So the first step is we say, okay, so we have 3 and we can start making a change by giving away 1 cent. We are left with 2 cents, then we can give away 1 more cent, we're left with 1 cent, and finally we can give away 1 cent and we are left with 0. So this is one way. Use all the ones. 1, 1, 1. Next iteration, we say, okay, let's consider coins 1 and 2. So here we were considering coin 1. Now we consider 1 and 2. What are the options? So again, we can start from 1 cent, and this is the exactly the same solution here, 1, 1, 1. But then we also have 2 coins which we can consider, and we basically return 2 coins. We're left with 1 coin, and we return 1 more cent, and we are left with 0. So the answer is 1, 1, 1, 2, and 1. And the last step, we say, okay, so now let's consider coins 1, 2, and 3. What's going to happen in this case? So in this case, we basically can start returning 1 cent in the exact same fashion. 1, 1, 1. We can start returning from, let's say, 3 cents, right? In this case, we're left with 0. And again, we can return 2 cents as in this solution, right? And we return 2 cents, we're left with 1 cent, and then we return 1 cent, and we are left with 0. So the answer is 3. 2, 1, 3, 1, 1, 1, right? Now, let's take a look at what's happening when we do have duplicates. The question that we are asking in here is how many ways to make a change of size 3 by using all coins at each step. So, step number 1, we say, okay, so what coins we have? 1, 2, and 3, right? What's the number of ways to make a change of size 1 first? So all we can do is return 1 cent, right? And we are left with 0. We can't use 2 and 3 cents, so we ignore them. The second step is 1, 2, and 3 coins again, and we're trying to find the total number of ways to make a change of size 2. What can we do here? We can return 1 cent. We're left with 1 cent. We already know how to solve the problem for 1 cent. We just return 1 cent, and this is one way. And the second way is we can return 2 cents. We can't return 3 cents here, so we ignore it. And the last step, we say, okay, so considering 1, 2, and 3 cents, how many ways to make a change of size 3? And here it's a little bit more interesting. So we start from 1 cent, right? We're left with 2 cents. And what's happening now, we already know how many ways to make a change of size 2. It's all of that, right? So we basically copy all of this over here. We are left with 1 cent here, 1, and then we are left with 0. And then we can also return this part, right? where we return 2 cents. So this is how we make a change of size 2. And what ends up happening is that to make a change of size 3, we can return 1, 1, 1, 1, or 1, 2. And then we start considering other coins. We start considering coin, let's say 2. In this case, we return 2 cents. We're left with 1 cent, right? And then we return 1 cent, and we are finally with 0 cents. And the last final step is we simply return 3 cents. Let's add it here, like so. And we are left with 0. And the total answer is going to be 4. 3 cents, first answer. The second answer is 2, 1. The third answer is 1, 2. And the last answer is 1, 1, 1. So as you can see, 2, 1 and 1, 2 were counted twice. This is why we have duplicates in this version of the algorithm. Hopefully it's not super confusing. Hopefully it was helpful. Let me know if you have any questions. And if not, thank you so much, guys. I'll see you soon. Bye.